All right, folks, this is the first topic in Unit 2A, and the last day I'll be out, so I will see you soon. We are talking about arithmetic and geometric sequences in this topic. So let's first define a sequence. A sequence is a function from the whole numbers to the real numbers. The whole numbers being 0, 1, 2, sometimes we refer to 1, 2, 3, 4, 5, 6, 7 as the natural numbers, but the natural numbers do not include 0, and we do allow 0. We aren't going to see negative inputs, so just positive or 0. Whole numbers, those counting numbers. 1.5 is not a possible input, but we can get any real number as the output. 1.5 can come out of the function, or an irrational number like the square root of 2. As a result, when we graph a sequence, it'll have points. But it'll look more like a scatter plot. We can't connect them to form a line or curve. These are what we call discrete functions. Our functions that we can connect might be referred to as continuous. Okay, so our first example, consider the sequence defined by a sub n equals 4 times n minus 3. This is sequence notation. It works very similarly to function notation. A is the name of the sequence. The subscript n is that input variable. So this is kind of like your f of x, and n is the x. So if we want to find a sub 1, we're going to plug 1 n for n. In for n. This is an explicit formula, so I can get any value out without needing another value. 4 times 7 is 28, minus 3 is 25. So a sub 1 equals 1, and a sub 7 equals 25 on this function, on this sequence. Now, this looks a whole lot like a linear function, right? It works very similarly. It does have constant increase between consecutive values of 4, and it starts with -3 first. Remember, those outputs can be anything, so the outputs could be negative, the inputs will not be. So in this course, we're focused on 2 types of sequences, arithmetic and geometric. That was an example of an arithmetic sequence, and we'll focus on these first. Arithmetics have successive terms have a common difference, and that's where we see that linear constant rate of change, okay? So here are 2 different forms. This is like slope-intercept form of a linear function. Slope-intercept. And this second one is like point-slope formula, point-slope. If you're not familiar with point-slope, find a Khan Academy video. It can definitely be helpful to understand how point-slope form works. A sub 0 refers to the initial term, or the 0th term. The D is the common difference. What are we counting by? And then a sub k represents the kth term. Frequently, if I want to know a sub n, a sub k is a prior term. A sub k is before n in the list, right? So typically the kth term is a term I know and I'm using to find another one. An arithmetic sequence behaves like a linear function, but they're not continuous. So increasing arithmetic sequence will increase equally each step. The slope is always the same, but it'll look like points, like so. If a sub 0 is 1, a sub 1 is 4, a sub 2 is 7. That's probably about all that's going to fit. So we would not connect this with a line. Do not connect the dots. The sequence does not exist between those dots. All right, so for example, let's look at these four and see if they are arithmetic or not. Take a moment, pause, see which ones you think are. All right, A has n squared. N squared is very clearly quadratic, right? That cannot be like a linear, so this would not be an arithmetic. Option B, this is an arithmetic because we have a constant difference and then a kind of y-intercept starting point. So we see that first power n, and so this is arithmetic. Let's make that nicer. The common difference, D, is -2, the slope that you can see from that linear form. Now we have an increase of 5, an increase of 5, an increase of 5, and an increase of 5. That is a constant, a common difference of 5, so this is arithmetic, where D equals 5. This is -3. This is +5. This is -7 and +9. That's not constant at all, and the signs are alternating, which is not possible for an arithmetic. So this is not arithmetic. All right, let's keep going. Example 3 says a sub n, let a sub n be an arithmetic sequence with a sub 3 equals 8 and d equals -3, d being that common difference. So we're told the third term has a value of 8 and the common difference is -3. So find an expression for a sub n and use it to find a sub 12. What we're going to do for arithmetic sequences, our formula that we do want to memorize is a sub n equals a sub k plus d times n minus k. But we want to understand what the mechanics of this are. Really what we're doing is we say, hey, this is the starting point. And then every time I move up in the sequence, if these are my pieces in the sequence, say this is a sub k and this is a sub n. If I go to the next one, I've added d once, I've added d twice, I've added d 3 times. So the difference between n and k, if this is the nth term and the kth term, the number of times I'm going to add that common difference is n minus k. And if I add over and over again, that is the definition of multiplication. So if I want to add a number 3 times, I just say times 3. So that's what's happening here. I say this is the number of jumps I took between those two terms, and that's the common difference times the number of jumps. That's how much I'm adding to where I started to get to where I'm going. So if I'm starting with a sub 3 and I want an expression for a sub n in general. So I'll start with a sub 3 and then add the common difference and say n minus 3 because where I'm starting is the third term. So let's plug in some of those known values. A sub 3 is 8. The common difference is -3. And n is that variable that we're going to let vary to go with a sub n. So if we want to find a specific term, like a sub 12, we'll then plug in 12 for n and be careful to obey order of operations here. I put my parentheses in silly places. There we go. So we're going to make sure that the 3, that multiplication, happens before the addition of the 8. So we have 8 minus 3 times 12 minus 3 is 9. 8 minus 3 times 9 is 27. 8 minus 27 is -19. All right. You try example 4. Try your hand at it, pause the video, see how it goes, and then come back to see if you figured it out. All right, example 4. If we want to find an expression for a sub n, but I don't have the common difference and I do have 2 terms, essentially the common difference is like the slope, yes? So we can use average rate of change to figure out our slope. So we can say 9 minus 7 over 6 minus 2. That's 2 over 4. That's 1/2. So our common difference will be 1/2 each time. Another method you could have done is plugging into your formula. We know 9 is the nth term. If we say this is a sub n and this is a sub k. A sub k, we start at 7 and we add our mystery common difference 6 minus 2 times. So essentially what we end up doing here is subtracting 7 from both sides. There's your 9 minus 7. And then dividing by 4. Do you see where I'm connecting these two things? Either way you approach it, you're finding slope. So the common difference is 1/2. So let's write our formula for a sub n. You can use either of your known terms. I'm going to start with the earlier one, but it doesn't matter which one you do. And minus, now make sure that the number you put here is the term number of the number you put here. So 7 is the second term, so what goes there is the second term. All right, and then I want to find a sub 24, so that is 24 minus 2. That's 1/2 of 22, so we have 7 plus 11, that's 18. All right. Example 5, the terms of an arithmetic sequence are shown above. Find an expression for a sub n and use it to find a sub 17. Now I can use any one of these as my known points, but essentially I need to figure out the slope of this set of points. I could pick any two because if I'm told it's an arithmetic, it's going to be the same no matter which two I pick, but I'll just do the first and the last. So the change in y is 0 minus 8 over 4 minus 0. This is negative 8 over 4. It dropped 8 and went over 4. So that is negative 2 is our common difference. And you can even see we go down by 2, down by 2, down by 2 each time we see consecutive points. So either way you approach that, our common difference is negative 2. So a sub n equals any one of these points can be my starting place. I'll use 8 is the first output plus the common difference. So I'll actually switch this to minus times n minus the term number. Well, the term number of 8 was 0, so it's just times n. And then if I want to do a sub 17, that's 8 minus 2 times 17. Again, you could have written this with any term number. It'll still work out the same. If you did a sub n equals 4 minus 2 times n minus 2, then you'd also end up with the same thing. So 17 times 2, that's 20 plus 14, so that is 34. 8 minus 34. And anytime I'm subtracting like that, I like to think about doing 34 minus 8 and then making it negative. So that is negative 26. Alrighty. Now let's talk about geometric sequences. Geometric sequences have a common ratio. Instead of adding the same thing each time, they are multiplying by the same thing each time. Constant proportional change. This is the big new topic. This unit focuses on exponentials, and next unit focuses on logarithms. So we need to get into this exponential growth situation. Now, geometric sequences will follow a discrete version of an exponential function, just not continuous. So we are increasing by a larger amount each time, but the percent increase will always stay the same. So when you see a geometric formula like this, we can plug in values. If I say g sub 0, anything to the 0 power is 1. So I have 8 times 1. If I go to g sub 1, that is 8 times 1/2. That's 4. That's the wrong spot. There we go. G sub 2, 8 times 1/2 squared. When you square a fraction, you square the top, square the bottom. 1 squared is still 1. So that is 8 times 1 over 2 squared. And 8 over 4 is 2. G sub 3, 1/2 cubed is 1 over 8. 8 over 8 is 1. And if I go to G sub 4, notice how the space between each spot is getting smaller each time. So we went down 1 unit in the last section. We're going to go down less than a unit in the next section, and even less, and even less, and even less, and even less. So G sub 4, 1/2 to the 4th power is 1/16. So that is 1/2. And they're just going to keep cutting in half. 1/4, 1/8, 1/16, 1/32. They get closer and closer to 0, but not. So if it were an exponential function, we could connect those dots and see that curve shape. But this is not an exponential function. It is a geometric sequence, so do not connect the dots. All right, look at those 4 examples. Decide if they're geometric, if they have a common ratio, pause, and then come back. All right, our first example is not geometric. Again, that's quadratic, and quadratics are not the same as exponentials. Not geometric. The second is geometric. It has a common ratio being raised to a power, and we have an initial term. This is actually the first term, and I should go back and make sure. We have initial term is our G sub 0. R is our common ratio, what we're multiplying by each time. And G sub k is the kth term. Typically that's a term we know that we're using to find another term. Okay, so this is geometric, and our common ratio R is that base being raised to some varying power. Now, if I want to see if a sequence of numbers is geometric, I'm going to take those numbers and find the ratio. I'm going to look at 3 over 1. The ratio was 3, so 1 times 3 gave me 3. I'm going to look at 2 over 3. The ratio is 2/3. 3 times 2/3 gives you 2. 6 over 2, 2 times 3 gives you 6. 4 over 6 is 2/3 again. 6 times 2/3 gives you 4. Notice we are seeing 2 ratios consistently, but they're not the same one every time. So this is not geometric. It's got to be the same one every time. Last but not least, -8 over 16 is -1/2. So 16 times -1/2. 4 over -8 is -1/2. So -8 times -1/2 is 4, positive 4. -2 over positive 4 is -1/2. So -4 times -1/2 is -2. Notice when my common ratio is negative, the signs are alternating. So this is geometric with a common ratio of -1/2. Negative ratio, alternating signs. Example 7, let's do this one. Our formula for a geometric is going to be similar, G sub n, G sub k, but this time we multiply because we are performing repeated multiplication. We're multiplying over and over and over again. So we take our G sub k, whatever that is, and to get further down in the sequence, if we're going to G sub n, we multiply by r, multiply by r, multiply by r. And if I multiply by r 4 times, that's the same thing as saying r to the 4th power, right? So the number of times I multiply is the difference between the term numbers. So I'm going to take my common ratio and multiply where I started by that common ratio this many times. That's the number of jumps. So if I have G sub 1 is 12 and the common ratio is 2, then I'll have n minus whatever the term number for 12 was, and that was 1. So n minus 1. Then I can use this to find G sub 4 by plugging in 4 for n. 2 cubed is 8, so this is 12 times 8. Excuse me. 12 times 8, 80 plus 16, 96. Excuse me, need a little water. Okay. All right, so We have a few more examples. You should pause the video and try these. Apply what we learned in arithmetics and the new formula and see if you can figure them out. And then these out together. So we have sequence shown above. We have several known points. So I can write g sub n equals, I'll go with g sub 2 equals 2 for this. G sub 2 is 2. I need my common difference, but I know the exponent will be n minus 2 because the term number was 2. And I'll color code that for us so we know which 2 gave us which thing. That blue's kind of dark. Let's just use pink. All right. So if we want to find our common ratio from the graph, we want to see what that change is each time, right? What are we multiplying by? My y values here are 8, 4, 2, 1, and what looks like 1/2. What's happening to these y values? Well, getting 4 from 8, 4 divided by 8 is 1/2, and 2 divided by 4 is 1/2, and 1 divided by 2 is 1/2. So our common ratio is 1/2. So there's our general form. If we want to use it to find g sub 10, we have 2 times 1/2 to the 10 minus 2 power. So that is 2 times 1/2 to the 8th power, 2 to the 8th. Notice we can simplify this just a little bit and not go all the way up to 2 to the 8th, because that's like 2 to the 1st over 2 to the 8th, which simplifies to 1 over 2 to the 7th using our exponential rules. And then 2 to any pretty high power is pretty easy to figure out, because we can do 2 times 2 times 2 and just count how many times we do it. So 2 times 2 is 4, that's 2 squared. To the 3rd is 8, to the 4th is 16, to the 5th is 32, to the 6th is 64, to the 7th is 128. So if you ever played the game 2048, 128, you'll be pretty familiar with powers of 2, because all of those numbers are powers of 2. If we want to find an equation with the geometric sequence with that given information, g sub n, we take our known term and we multiply it by the common ratio to the power of the difference in the term numbers. So the term I'm trying to find minus the term I used and started with, which was the 3rd term, g sub 3. All right, last example in this section, g sub 2 equals 24 and r is 1/2. Find the expression and then find g sub 5. So g sub n should be 24 times 1/2 to the n minus 2, since 24 was the 2nd term. And then if we want to use this to find g sub 5, we'll do 24 times 1/2 to the 5 minus 2. That is, I'm doing 1/2 cubed. And that is 1 over 2 cubed, which is 8. 24 divided by 8 is 3. All right. These are our last 2 examples, and this is our situation where we're given 2 terms but not the common ratio, and we have to figure out our common ratio. We can write an expression using our formula. We know g sub n equals g sub k times r to the n minus k. And think about the earlier one as the g sub k and the later one as the g sub n. So if I know that 128 happens when I start at -2 and multiply by this missing common ratio this number of times, which will be 6 minus 3, the difference in those term numbers, I can solve this equation for r, right? This is 128 equals -2 times r to the 3rd. If I'm solving for r, I need to isolate r, first dealing with the multiplication. So I have r cubed, and I'm switching sides just to make it nice, but this is negative 64, 128, 64. And then we take the cube root of both sides. Whatever power r is raised to, we're taking the cube root, or that type of root. We can take the cube root of a negative number, so because 3 negatives multiplied together equal a negative. So, and this is looking for what number times itself 3 times is the cube root of 64, and that is -4. So our R value is -4. Our G sub n, we can use either value for K, but I'll just stick to -2. -4 is my R, and then n minus 3, because -2 was the third term. And I'm just going to scoot this down here. If I want to find G sub 11 from this, I'm going to plug in 11. 11 minus 3 is what I'm raising -4 to. So that is -4 to the 8th power. That's a little bit big to figure out on our own. Sometimes these will be calculator questions, or I'll just try and keep the numbers pretty. But we have -4, be sure to use parentheses or drop the negative because it's an even power, but better off using parentheses, times -2. This gets pretty large, so times -2. Our result is -131,072. All right. Now that you've seen one, definitely, if you weren't able to figure it out earlier, pause and try this second one now that you have an example to go off of, and then come back and see if it's right. So if I need to find my R, I'm going to set up my equation. 1.5 equals 48 times R to the 7 minus 2. So I'm looking at 1.5 over 48 equals R to the 5th. So R will be the 5th root of 1.5 over 48. And I do not expect you to do that without a calculator. So we're going to do the 5th root. In Desmos, you have to go to the Functions tab and scroll until you find the nth root, and then you can type in the 5th root, 1.5 over 48. And that is exactly 1/2. In the TI calculator, to get the 5th root, you'll go to Math, and then use what on my calculator is option 5, it's the nth root. So you can do n, and then alpha x will give you a fraction. 1.5 over 48 is also 1/2, either way. All right, so if we want to use that to find our G sub n in general, this time maybe I'll start with the 1.5, 1/2 to the n minus 7. G sub 11 will be 1.5 times 1/2 to the 11 minus 7. So 1.5 times 1/2 to the 4th power. And we know 2 to the 4th power is 16. So this is times 1 over 16. 1.5 is just 3/2. So I actually can do this by hand. 2 times 16 is 32. So this is 3 over 32. And 3 and 16 do not have any common factors, so 3 over 32 does not either. That is our fully simplified form. Alrighty, folks, that is all for 2.1. Thanks for hanging in there, and be sure to practice.